Welcome to Mahatma Education Society's e-learning channel. This is the 17th of a series of lectures on Introduction to Mechanical Vibrations, and we are in the chapter Free and Damped Single Degree of Freedom Vibration Systems, and we are continuing with the solution of numericals. In this example, we have a step rotor of small radius r and capital radius, that is a bigger radius 3r, and the mass is given to us as capital M, and the mass moment of inertia is I about O axis, and it is rolling over a surface, flat surface, where there is no slip between the two surfaces, and we have a block of mass M and moving with a displacement x, right, and there are some springs K1, K2 and K3, right, and we are required to find out the equivalent system parameters, and because only x is given to us here, so that will be the basic coordinate, and these are the values that we are supposed to get in kilograms, that is M equivalent, and this one is K equivalent in Newton per meter. So let me start with the kinetic energy. Ke is equal to half times the mass, okay, M into x dot squared, right, and the other one is the rotor, and because the CG also is shifting its position, right, as it rolls on, the oscillation will be about the point of contact here, that is, let us say it is point P. So what is the kinetic energy for that? So it is plus half times I about P into let me say that the angle of oscillations is theta, right, theta dot squared, and this should be equal to half times M times x dot squared plus half times. So how should I write this? I about P, that is I about CG, that is CG is nothing but O axis here, that is given as I about O. So may not be required for the step rotor to break it, right. So in terms of mr square by 2 for small cylinder, that is not required here. Directly you can write in terms of I about O axis, right, and plus, so I want to transfer the moment of inertia from its own center of gravity axis O to the P axis, that is the point of contact. So I am trying to use the parallel axis theorem here. So what is that here? I about O plus the mass, nothing but capital M, into distance between this axis and the point P, square of that, so which is nothing but 3r. So this is 3r and square of this, okay, theta dot squared. So I about O axis plus the mass into distance between the two axes squared, right. So what is the relation now between x and theta? What is that? So from here the moment of mass M is x, right, so this also is a x, right, and over here for the point O or the axis O, the moment is how much in terms of theta about point P? It should be 3r, that is radius times theta, that is the arc distance, right. So which is nothing but basically this also is x equal to 3r theta for this particular point over here on the periphery, right. So the distance moved by point O, that is 3r theta, should also be equal to x only, the same thing as this, okay, agreed. So this is x. So I am having x equal to 3r theta, or theta should be equal to x by 3r. I want to convert theta in terms of x, so theta dot should be equal to x dot by 3r, right. So this should be half times M times x dot squared plus half times I about O axis plus M into 3r squared, and theta dot is nothing but x dot divided by 3r squared of this, and then you can write this something like half into something of x dot squared, where this you can combine this one, right, M for this one, plus, so in this case I am having 9r squared, right, and if I take it inside I am having I naught upon 9r squared, plus in this case I am having 9r squared over here, 9r squared over here, that will be cancelled out, it will be capital M. So this should be half times capital M plus small m, okay, plus I naught upon 9r squared into x dot squared. And if I compare this with the Ke of the equivalent system, I have half into m equivalent into x dot squared. So this term within the bracket should be m equivalent in kilograms. Okay, so this is what we get. Now let us talk about potential energy, right? So I'm having 3 springs. So let me write for the first spring K1 half into K1 into x squared. The deformation is x only for this spring, plus the spring of stiffness K2 is also having moment of x only, because it is one and the same thread over here, that is bond over here, connected to mass m. So it should be half times K2 x squared. And what about K3 now? What is the amount of deformation happening to spring, okay, having stiffness K3? Now I know that point O, or the CG of the rotor, is moving by an amount equal to x in the left direction. So this one is x, right? So this is an idler pulley, doesn't have any mass, only meant for transmitting the motion. So this should also be x over here, right? So one end of the spring of stiffness K3 is moving by x in the right. So what is the amount moved by this particular point over here, left end of the spring, right? So this particular point on the rotor will be having an arc moment, right, compared with the point P over here, the contact point. It acts like a pivot, right? So this 3r plus r is how much? It is 4r, 4r times theta, okay. So 4r theta is the distance moved by this particular point over here, okay. And what is that here, 4r theta? That is 4r into theta is nothing but x upon 3r. So I write here x upon 3r, and r will be cancelled out, it will be 4 upon 3x. So this distance will be 4 upon 3 times x. So total amount of deformation for this spring is how much? X over here, and over here it is 4 upon 3x on this side. So total amount of deformation is x minus of minus 4x upon 3, that is how much? X plus 4x upon 3. So 1 plus 4 upon 3x, okay. So deformation is how much here? 7 by 3x, right? So I want here the contribution from the spring of stiffness K3, it should be half times stiffness is K3 and 7 by 3 x squared of this, okay. So I just combine them into half into something of x squared. So I am having K1 plus K2 plus, so it is 49 by 9 K3 x squared. The term within the bracket should be K equivalent, that is Newton per meter, right? So this is what we get. In this example we are having inverted pendulum, where the CG of this lever is above the pivot axis O, and in the second case I am having the CG that is below the axis A. So it is something kind of a normal pendulum, right? So let me focus on the part A first. We are required to find out the time period of small oscillations. So let us assume that the amount of oscillations is theta in both cases, small values, right? So let me write the kinetic energy, okay. So what is that? Half into mass moment of inertia about O axis into theta dot squared is equal to half into I about O axis is nothing but I about CG axis plus mass of the lever into distance between the CG axis and the pivot. What is that here? So from G to the end it is L by 2 minus this L by 3. So L by 2 minus L by 3 is how much? L by 2 minus L by 3. That should be 3L minus 2L upon 6, that is L by 6, right? So it is L by 6 square of this. So I am trying to apply the parallel axis theorem, right? What is I about CG axis here for the lever, assuming small cross section dimensions? So it should be ml square by 12. So ml square by 12 plus ml square by 36 theta dot squared, right? this should be equal to, so I want the common denominator, so this should be 12 3 is 36 and 3 times, so 3 plus 1 is 4 by 36, that is ml square by 9, ml square by 9 theta dot squared, and this ml square by 9 is nothing but I equivalent kilogram meter squared, right? Now what is potential energy? Potential here in this case is by virtue of the spring as well as the lever, right, acting like a pendulum. In this case it is a inverted pendulum, so it should be giving me a negative potential. So let me write first for the spring, so half times k times the deformation of the spring squared of that. So what is the deformation? That is from point O to this spring. What is the distance here? It is 2l by 3, so 2l by 3 theta, that is the amount of deformation squared of this, agreed? Plus, now what is the amount of potential as given by the lever? So it's a case of inverted pendulum, so it is giving me a negative potential. So instead of this plus I have minus value mg into the height difference of the center of gravity g when it oscillates. So this will be something like this, right? So what is the height difference here? It is L upon 6 minus L upon 6 cos of theta, right? So it is L upon 6 in brackets 1 minus cos theta, and you know this, what is 1 minus cos of theta? It should be half times theta squared. So we had seen number of numericals on this, so P should be given as half times. So let me write this in the brackets. What is that? 4 kl square by 9, right, minus it should be mg l by 6 and theta square over here, and this term within the bracket should be kt equivalent Newton meter per radians. Fine. Now what is the time period now? Tp is equal to 2 pi by omega n, or this is 2 pi under root of, what is that, I equivalent divided by kt equivalent, and when you put these values and simplify it further, you get the result something like this. So it's a homework for you, you try to verify, right? And in the next case I am having, so what is kinetic energy for the second part? So it's basically half into I about the a axis, right? Ke is equal to half into I about a axis into theta dot squared. Fine. And what is that here? Half into I about cg axis plus the distance between the cg axis and this square of that. So again I am having this distance as L upon 2 minus L upon 3, it's L upon 6, right? So it is m into L upon 6, right, square of that theta dot squared, and basically you end up with the same thing, right? So I will write directly here I equivalent equal to ml squared by 9 kilogram meter squared, right? And what is potential energy now? So this is a case of a normal pendulum, compound pendulum, right? So half into k for the spring into deformation square. Now deformation over here is how much? L upon 3 into this L upon 3 into theta, because the pivot has been shifted, right, squared, and this one lever will be giving me a positive potential now, so it should be plus over here, right, and this should be mg into L upon 6 into 1 minus cos of theta. So basically this will be half times kl square by 9 plus mg L by 6 into theta squared, and this should be your kt equivalent for the second part, right? And again incorporating this formula, Tp or the time period for one oscillation is 2 pi under root of I equivalent by kt equivalent, you should come across this particular answer. Okay. In this example we have a ring of mass m suffix r, and the radius of the ring is capital R, and we have a bar of mass mb, and we have a block of mass m that is at distance small l from the center of the ring, and this block of mass m can be adjusted anywhere along the length of the bar, and the entire system is oscillating about the contact point P, right? And we are required to find out for small oscillations of the system what is the natural frequency, and we are supposed to get this particular value, right? Now let us start with the kinetic energy of the system, Ke. Now let me write for the ring. It's a kind of a torus, right? So half into the I about point P into theta dot squared, right? So theta is the angle of oscillation, and plus half into the mass moment of inertia about point P for a bar. So this is for the bar. Now this should be for the ring, right? Into theta dot squared plus half into I about P into theta dot squared for the block of mass, right? And this should be equal to half into for the ring. What is that? So we have I about its center of gravity, which is nothing but the mass into radius squared, right? So mr into radius squared, that is about its center of gravity. Let us call it as O axis for the ring, and I want to transfer that mass moment of inertia from O axis towards point P, or the P axis, which is nothing but the again plus mass into distance between the two, which is again r squared into theta dot squared, right? So this should be 2 times mr into r squared, right? Plus for the bar, so we have half times what is I about Cg of the bar, that is equal to mass of the bar into the length square divided by 12, right? Assuming that cross section dimensions of the bar are very small compared to the length. So what is the length of the bar? It is nothing but twice of the radius of the ring. So it is 2r, that is the length, right? So mass into length square divided by 12, fine. That is about its center of gravity axis, that is O axis here, and I want to transfer the moment of inertia. So plus mass of the bar into distance between the Cg of the bar and the contact point square of that one, which again is a r here, and square of this into theta dot squared, right? Plus let me write for the block now. So initially the contact point was over here, right? So this is the original contact point. Now the contact point is over here. So this amount of theta has been shown to be exaggerated. We are trying to assume that theta is very, very small. So distance between this point P and this initial position, okay, that is very, very small, okay. So half into what is the mass moment of inertia of the block of mass m about point P, the new position, it should be half into mass m into the mass moment of inertia into what is that, distance between the two, square of that one, what is that. So if this point, original point, would have been over here, right? So this would have rested something like this, right? And what is the distance, this one, that is equal to this capital R minus this length L, right? So this should be R minus length L, fine. So m into r minus small l, that is the distance and square of that one. So I'm trying to apply the definition of mass moment of inertia, right? So we get a mass moment of inertia about point P into theta dot squared, right? And now you can combine everything, right? So this is 2 times mr into r squared plus, so I'm having mbr square over here and mbr squared, So we have here 4 divided by 12, that is 1/3. So 1/3 plus 1, that is 4 by 3, right? 4 by 3, right? MBR squared, fine. And what about here? So this is plus m into r minus small l square of this theta dot squared, right? So this entire thing within the brackets should be I equivalent in kilogram meter squared, right? Let me write the equation for potential energy. Okay, so for the ring there is no change in the potential, right? And for the bar also the center of gravity remains at same level, so there is no contribution of the bar, right, in the calculation of potential energy. So only change is by virtue of the block of mass m. So what is the expression for this, right? So initially this was mass was over here, and then it has gone something like this upwards, right? So it behaves like a simple pendulum, right? So m into g into what is that, high difference. So earlier it was something like this, and then it has been like this, right? Okay, so it should be L into 1 minus cos of theta, and basically if theta is very small, this is nothing but half times theta squared. We had already seen all these things, so this should be half times mgl and theta squared, and the term within the brackets is nothing but kT equivalent in Newton meter per radians, fine. And omega n should be under root of kT equivalent upon I equivalent, and basically this is what is the answer that we are getting. So we are strongly advised to construct such devices, and whether your formulation for the natural frequency or time period is correct or not. So you can actually do an experiment for different values of small l, and try to measure the masses. Okay, take all these values and do a practical test, and then try to correlate your answers with the theoretical results. Then you can be sure of your answers. Now the last one is some small modification, okay, compared to the earlier one. Now what we are having is a block is added m1, right, at distance l1. Okay, so the initial mass of the block m has been replaced by m2, and small l has been replaced by l2 over here. Okay, so we make the corresponding changes here also, and what is the contribution of this one. Okay, so we can add that one over here. Okay, so if we are trying to refer the earlier formula, okay, so we have replaced this small l by l2 and small l by l2 over here, small m by m2, right, something like this, and these are the additional contributions from this particular mass, that is m1. Okay, so this mass m1 will be having a negative potential, so there will be a minus over here, minus, and mg L1, okay, m1gl1. So that is the contribution in the potential energy. And for kinetic energy, we have the mass moment of inertia of this mass m1 with respect to the contact point P, which will be half times the mass 1 into what is that, the distance between the contact point and this one, square of that one. So because I am having, this is mass m1, so this is r, and this distance is l1, so r plus l1, that is the distance, and I want the square of that one. So mass into the square of the distance, second moment of mass, becomes the mass moment of inertia into the theta dot squared. So this is the contribution in the kinetic energy for the mass m1, right. So I am having that particular term added up over here in the kinetic energy, and other terms will remain same, right. So it is r plus l1. So I hope you understood the contents, and we will have some additional numericals solved in the coming lectures. Thank you.